A shock absorber is a mechanical or hydraulic device designed to absorb and damp shock impulses. It does this by converting the kinetic energy of the shock into another form of energy which is then dissipated. Most shock absorbers are a form of dashpot. Description: pneumatic and hydraulic shock absorbers are used in conjunction with cushions and springs. An automobile shock absorber contains spring-loaded check valves and orifices to control the flow of oil through an internal piston. 1. Design consideration: when designing or choosing a shock absorber is where that energy will go. In most shock absorbers, energy is converted to heat inside the viscous fluid. In hydraulic cylinders, the hydraulic fluid heats up, while in air cylinders, the hot air is usually exhausted to the atmosphere. In other types of shock absorbers, such as electromagnetic types, the dissipated energy can be stored and used later. In general terms, shock absorbers help cushion vehicles on uneven roads. Vehicle suspension: in a vehicle, shock absorbers reduce the effect of traveling over rough ground, leading to improved ride quality and vehicle handling. While shock absorbers serve the purpose of limiting excessive suspension movement, their intended sole purpose is to damp spring oscillations. Shock absorbers use valving of oil and gases to absorb excess energy from the springs. Spring rates are chosen by the manufacturer based on the weight of the vehicle, loaded and unloaded. Some people use shocks to modify spring rates, but this is not the correct use. Along with hysteresis in the tire itself, they damp the energy stored in the motion of the unsprung weight up and down. Effective wheel bounce damping may require tuning shocks to an optimal resistance. Spring-based shock absorbers commonly use coil springs or leaf springs, though torsion bars are used in torsional shocks as well. Ideal springs alone, however, are not shock absorbers, as springs only store and do not dissipate or absorb energy. Vehicles typically employ both hydraulic shock absorbers and springs or torsion bars. In this combination, shock absorber refers specifically to the hydraulic piston that absorbs and dissipates vibration. Now, composite suspension systems are used mainly in two-wheelers, and also leaf spring are made up of composite material in four-wheelers. Early history. In common with carriages and railway locomotives, most early motor vehicles used leaf springs. One of the advantages of these springs was that the friction between the leaves offered a degree of damping, and in a 1912 review of vehicle suspension, the lack of this characteristic in helical springs was the reason it was impossible to use them as mainsprings. However, the amount of damping provided by leaf spring friction was limited and variable according to the conditions of the springs, and whether wet or dry. It also operated in both directions. Motorcycle front suspension adopted coil-sprung Druid forks from about 1906, and similar designs later added rotary friction dampers, which damped both ways, but they were adjustable. These friction disc shock absorbers were also fitted to many cars. One of the problems with motor cars was the large variation in sprung weight between lightly loaded and fully loaded, especially for the rear springs. When heavily loaded, the springs could bottom out, and apart from fitting rubber bump stops, there were attempts to use heavy mainsprings with auxiliary springs to smooth the ride when lightly loaded, which were often called shock absorbers. Realizing that the spring and vehicle combination bounced with a characteristic frequency, these auxiliary springs were designed with a different period, but were not a solution to the problem that the spring rebound after striking a bump could throw you out of your seat. What was called for was damping that operated on the rebound. Although C.L. Horrock came up with a design that had hydraulic damping in one direction only in 1901, it does not seem to have gone into production right away. whereas mechanical dampers such as the Gabriel snubber started being fitted in the late 1900s. These used a belt coiled inside a device such that it freely wound in under the action of a coiled spring, but met friction when drawn out. Gabriel snubbers were fitted to an 11.9 HP Arrol Johnston car which broke the 6-hour Class B record at Brooklands in late 1912, and the Automotor Journal noted that this snubber might have a great future for racing due to its lightweight and easy fitment. One of the earliest hydraulic dampers to go into production was the Telesco shock absorber, exhibited at the 1912 Olympia Motor Show and marketed by Polyho Carburetors Limited. This contained a spring inside the telescopic unit like the pure spring-type shock absorbers mentioned above, but also oil and an internal valve so that the oil damped in the rebound direction. The Telesco unit was fitted at the rear end of the leaf spring in place of the rear spring to chassis mount, so that it formed part of the springing system, albeit a hydraulically damped part. This layout was presumably selected as it was easy to apply to existing vehicles, but it meant the hydraulic damping was not applied to the action of the main leaf spring, but only to the action of the auxiliary spring in the unit itself. The first production hydraulic dampers to act on the main leaf spring movement were probably those based on an original concept by Morris Houdai, patented in 1908 and 1909. These used a lever arm which moved hydraulically damped vanes inside the unit. The main advantage over the friction disc dampers was that it would resist sudden movement but allow slow movement, whereas the rotary friction dampers tended to stick and then offer the same resistance regardless of speed of movement. There appears to have been little progress on commercializing the lever arm shock absorbers until after World War I, after which they came into widespread use, for example as standard equipment on the 1927 Ford Model A. Types of vehicle shock absorbers. Most vehicular shock absorbers are either twin-tube or monotube types with some variations on these themes. Twin-tube Basic twin-tube, also known as a two-tube shock absorber. This device consists of two nested cylindrical tubes, an inner tube that is called the working tube or the pressure tube, and an outer tube called the reserve tube. At the bottom of the device on the inside is a compression valve or base valve. When the piston is forced up or down by bumps in the road, hydraulic fluid moves between different chambers via small holes or orifices in the piston and via the valve, converting the shock energy into heat which must then be dissipated. Twin-tube gas-charged, variously known as a gas cell two-tube or similarly named design. This variation represented a significant advancement over the basic twin-tube form. Its overall structure is very similar to the twin-tube, but a low-pressure charge of nitrogen gas is added to the reserve tube. The result of this alteration is a dramatic reduction in foaming or aeration, the undesirable outcome of a twin-tube overheating and failing, which presents as foaming hydraulic fluid dripping out of the assembly. Twin-tube gas-charged shock absorbers represent the vast majority of original modern vehicle suspensions installations. Position-sensitive damping, often abbreviated simply as PSD. This design is another evolution of the twin-tube shock. In a PSD shock absorber, which still consists of two nested tubes and still contains nitrogen gas, a set of grooves has been added to the pressure tube. These grooves allow the piston to move relatively freely in the middle range of travel and to move with significantly less freedom in response to shifts to more irregular surfaces when upward and downward movement of the piston starts to occur with greater intensity. This advance allowed car designers to make a shock absorber tailored to specific makes and models of vehicles and to take into account a given vehicle's size and weight, its maneuverability, its horsepower, etc., in creating a correspondingly effective shock. Acceleration-sensitive damping. The next phase in shock absorber evolution was the development of a shock absorber that could sense and respond to not just situational changes from bumpy to smooth, but to individual bumps in the road in a near-instantaneous reaction. This was achieved through a change in the design of the compression valve, and has been termed acceleration-sensitive damping, or ASD. Not only does this result in a complete disappearance of the comfort versus control trade-off, it also reduced pitch during vehicle braking and roll during turns. However, ASD shocks are usually only available as aftermarket changes to a vehicle and are only available from a limited number of manufacturers. Coilover shock absorbers are usually a kind of twin-tube gas-charged shock absorber around which has been mounted a large metal coil. Though common on motorcycle and scooter rear suspensions, coilover shocks are uncommon in original equipment designs for vehicles, though they have become widely available as aftermarket add-ons. Coilover shocks for cars have been considered specialty items for high performance and racing applications where they allow for significant reductions in overall vehicle height, and though high-quality aftermarket options with wide sturdy springs may provide improvements in vehicle performance, there is dispute over whether or not most aftermarket coilover shocks confer any material benefits to most drivers and may in fact reduce performance over original equipment installations. Monotube. The principal design alternative to the twin-tube form has been the monotube shock absorber, which was considered a revolutionary advancement when it appeared in the 1950s. As its name implies, the monotube shock, which is also a gas-pressurized shock and also comes in a coilover format, consists of only one tube, the pressure tube, though it has two pistons. These pistons are called the working piston and the dividing or floating piston, and they move in relative synchrony inside the pressure tube in response to changes in road smoothness. The two pistons also completely separate the shock's fluid and gas components. The monotube shock absorber is consistently a much longer overall design than the twin tubes, making it difficult to mount in passenger cars designed for twin-tube shocks. However, unlike the twin tubes, a monotube shock can be mounted either way. It does not have any directionality. It also does not have a compression valve, whose role has been taken up by the dividing piston, and although it contains nitrogen gas, the gas in a monotube shock is under high pressure, which can actually help it to support some of the vehicle's weight, something which no other shock absorber is designed to do. Mercedes became the first auto manufacturer to install monotube shocks as standard equipment on some of the cars starting in 1958, manufactured by Bilstein. Because the design was patented, no other manufacturer could use it until 1971 when the patent expired. Theoretical approaches. There are several commonly used principles behind shock absorption. Hysteresis of structural material, for example the compression of rubber discs, stretching of rubber bands and cords, bending of steel springs, or twisting of torsion bars. Hysteresis is the tendency for otherwise elastic materials to rebound with less force than was required to deform them. Simple vehicles with no separate shock absorbers are damped, to some extent, by the hysteresis of the springs and frames. Dry friction is used in wheel brakes, by using discs at the pivot of a lever, with friction forced by springs. Used in early automobiles such as the Ford Model T, up through some British cars of the 1940s, although now considered obsolete. An advantage of this system is its mechanical simplicity. The degree of damping can be easily adjusted by tightening or loosening the screw, clamping the discs, and it can be easily rebuilt with simple hand tools. A disadvantage is that the damping force tends not to increase with the speed of the vertical motion. Solid-state, tapered chain shock absorbers, using one or more tapered, axial alignment of granular spheres, typically made of metals such as nitinol, in a casing. Fluid friction, for example the flow of fluid through a narrow orifice, constitutes the vast majority of automotive shock absorbers. This design first appeared on Most racing cars in 1902. One advantage of this type is by using special internal valving, the absorber may be made relatively soft to compression and relatively stiff to extension, controlling rebound, which is the vehicle response to energy stored in the springs. Similarly, a series of valves controlled by springs can change the degree of stiffness according to the velocity of the impact to rebound. Specialized shock absorbers for racing purposes may allow the front end of a dragster to rise with minimal resistance under acceleration, then strongly resist letting it settle, thereby maintaining a desirable rearward weight distribution for enhanced traction. Compression of a gas, for example pneumatic shock absorbers, which can act like springs as the air pressure is building to resist the force on it. Enclosed gas is compressible, so equipment is less subject to shock damage. This concept was first applied in series production on Citroën cars in 1954. Today, many shock absorbers are pressurized with compressed nitrogen, to reduce the tendency for the oil to cavitate under heavy use. This causes foaming, which temporarily reduces the damping ability of the unit. In very heavy-duty units used for racing or off-road use, there may even be a secondary cylinder connected to the shock absorber to act as a reservoir for the oil and pressurized gas. In aircraft landing gear, air shock absorbers may be combined with hydraulic damping to reduce bounce. Such struts are called oleostruts. Inertial resistance to acceleration. For example, prior to 1966, the Citroën 2CV had shock absorbers that damp wheel bounce with no external moving parts. These consisted of a spring-mounted 3.5 kg iron weight inside a vertical cylinder and a similar to, yet much smaller than versions of the tuned mass dampers used on tall buildings. Composite hydro-pneumatic suspension combines many suspension elements in a single device: spring action, shock absorption, ride height control, and self-leveling suspension. This combines the advantages of gas compressibility and the ability of hydraulic machinery to apply force multiplication. Conventional shock absorbers can be combined with air suspension springs, an alternate way to achieve ride height control, and self-leveling suspension. In electrological fluid damper, an electric field changes the viscosity of the oil. This principle allows semi-active dampers application in automotive and various industries. Magnetic field variation. Magnetorheological damper changes its fluid characteristics through an electromagnet. The effect of a shock absorber at high frequencies is usually limited by using a compressible gas as the working fluid or mounting it with rubber bushings. Features and amp benefits. Some shock absorbers allow tuning of the ride via control of the valve by a manual adjustment provided at the shock absorber. In more expensive vehicles, the valves may be remotely adjustable, offering the driver control of the ride at will while the vehicle is operated. The ultimate control is provided by dynamic valve control via computer in response to sensors, giving both a smooth ride and a firm suspension when needed, which allow ride height adjustment or even ride height control, seen in some large trucks and luxury sedans, including Lincoln and Land Rover automobiles. Ride height control is especially desirable in highway vehicles intended for occasional rough road use, as a means of improving handling and reducing aerodynamic drag by lowering the vehicle when operating on improved high-speed roads, as seen in the Tesla Model S. Bibliography. Skinner, Vikram K. Wolfenden, Alan M. 3D, Mechanics and Mechanisms of Material Damping, ASTM Special Technical Publication Number 1169, Philadelphia, Pennsylvania, USA, ASTM International, ISBN 978-0803114951. Holland, Max. When the Machine Stopped, A Cautionary Tale from Industrial America. Boston, Harvard Business School Press, ISBN 978-087584-208-00 CLC 246343673.